And that's 78 tokens per second. Solid for a model this size on this hardware. See, that's usually what I do on this channel. Speed between different kinds of hardware. But what about quality of code output? That's not an easy problem. It's not like saying hi to a model or asking it to write a story. I've avoided talking about code quality for a while because there's so many different kinds of devs out there, so many different code bases, different LLMs, that creating an objective set of tests that suits everyone is pretty much impossible. Well, in this video, I'm sharing a benchmark with you. It's new, and you can run it on your own code base against your own model picks. I'm gonna show you how to use it and walk you through some examples. So, when you give your model your file, is it actually reading it? And does it know when to stop? There's a leaderboard later in this video that's gonna tell you to pick the wrong model, and I'm gonna show you why. Now, I'm open sourcing this tool, but I didn't come up with it. I kind of stole it. Or more accurately, I was heavily inspired by this channel, Protoricus. What? 6,000 subscribers? Everybody should go and subscribe to him right now. I caught a few recent videos of his where he was running the latest Qwen and Gemma models against his own code base using a really clever tool. The only downside is that it's not open source and he hasn't shared it yet. So I had the idea to reverse engineer that concept and make it generic enough to work on any code base with configurable file selection options with glob patterns, add charting on top of it, and put it on GitHub for free. Oh, and by the way, if you go to my channel's homepage, I've added a little section down here where I highlight small YouTube channels I think are awesome and genuinely valuable. So go show them some love. Now here's what the benchmark actually does. It drops an entire source file into the model's context. Then it asks the model to verbatim reproduce the first 20 lines of one specific function in that file. Like this one, for example, at line 10,141. Why verbatim? Well, if the model genuinely is reading the file, the answer is in there. If it's hallucinating or guessing from the training data, the lines won't match up. And it does this for a sample of functions picked from varying depths in the file. So line 200, line 2000, line 8000, and so on. We're basically testing recall at depth, not just at the top. The exact number is configurable. So for example, I have a small Python file here. This one has 11 functions. I set K to 16, so it'll do 11. jQuery, K set to 16, but jQuery has a lot more functions than that. And here's the part most benchmarks miss. 2 metrics, not 1. Matched will be the expected lines the model produced in order, and hallucinated is the extra lines the model invented that aren't in the file. So a model that scores 20 out of 20 with 65 hallucinations is not the same as one that scores 13 out of 20 with only 1 hallucination. The grading is deterministic. Plain line level diff. I'm not sending this to an LLM to be the judge. Both columns are computed and not estimated. And yeah, I spent a couple of days with LM Studio running this benchmark, which by the way, I called Code Needle. Huh? Code Needle? It's clever, right? All right. Maybe not. Maybe not so clever. Downloaded a bunch of these models, some of the newer ones like Gemma 4, Qwen 3.6, Qwen 3.5, Dense, and MOE models. And I started noticing some weirdness. For example, Gemma was failing miserably. And also models that were reasoning, they were burning the whole output budget on thinking tokens. Of course. That's usually the problem that we run into with benchmarks of thinking models. Also, did you know that in LM Studio, this model right here, Qwen 3.4b, you can load up to a maximum of context length of 32,000, but if you use the LM Studio CLI and you specify the context length, you can actually specify more than that. So LM Studio's UI is actually kind of lying about that being available. It's outlining it in red, but it's not gonna run at all. So I needed to turn off thinking, and I eventually provided that by using models config, part of the tool. So you can configure the different parts of your model, the base URL, the name, the API key, temperature, max tokens, and finally this one, suppress thinking. So all this was fine, but there's one debugging moment that really mattered and stood out here because it changed how I understood what this benchmarking is really measuring. And Protoricus, I don't know how to say that. Sorry, Protoricus. He actually ran into similar issues on his latest tests of Gemma 4 because Gemma 4 behaves a little bit differently. A lot of these AI agent tools sound great right up until you have to actually deploy them. If you like the idea of autonomous AI doing useful tasks in the background, Gobii is built for that. A lot of people want AI automation, but not the extra server maintenance and patching that comes with it. Gobii feels like the version for people who want the outcome, not the side project to maintain, and it gives you a way to spin up autonomous AI colleagues that keep working in the background for you. The setup is simple. Go to gobii.ai, create create a colleague, give it a task, and let it run. I tried it myself and got going in just a couple of minutes. I set up an AI colleague to grab the top 3 Hacker News posts, then summarize each one and send it to me every morning. Mine doesn't just send me text summaries either. It also sends me a voice readout. Kind of feels like a little personalized podcast.
Hey Alexander, here's your perky Hacker News briefing for today.
All that from one prompt. The biggest thing here is that Gobii makes autonomous AI feel usable instead of complicated. And there's real traction here too. It's open source, enterprise proven, and already being used by some well-known teams. Check it out to see if it fits your workflow. Visit Gobii AI using the link in the description, pick a use case, and deploy your first colleague in just a few minutes. Now first, I wanted to answer the age-old question of how different is the BF16 quantization versus like an MLX int4 quantization? Is that going to give us significantly different quality of results? So I got both of those models, BF16 and the 4-bit of Gemma 4 31B. This is the dense model. And by the way, I'm currently running this on the 128 gigabyte unified memory M5 Max MacBook Pro. So you'd think that 58 gigabytes would be enough, but no. It's not. When you bump up the context, you load the model, I'm at 91 gigabytes already out of 128. But guess what happens when you throw jQuery at it, which is 10,000 line file? jQuery, there it is, processing the prompt, and notice how long that takes. Yeah, we're at 9% still of processing just the prompt. And check out the memory. Yeah, we're at 100 gigs now already. This is like real world stuff right here, not the speed benchmarks that we usually do. Speed benchmarks are important, they have their own place, but this right here is you throwing an actual code base at a model and seeing how it works. This is what frontier models are really good at, fast prompt processing. This is what big chunky GPUs are good at too. 44%, 106 gigabytes and growing. So you can imagine this doesn't go on for that much longer. And what did my data show? Well, 4-bit was somehow better than full precision. And that can't be right? No, that's not what it was. So space wasn't the only difference, neither was the quality. Gemma, being a little bit different, it strips class method indentation when it emits code. In other words, it knows the answer, it just renders it with 0 indent. So the two quantizations were rendering white space slightly differently, and I needed to account for that in the benchmark. So this benchmark wasn't only measuring recall, it was also exposing how each model renders code, a behavior that kind of nobody talks about or documents. So how do you set this up for yourself? Well, you go to this repository, you give it a star. You don't have to give it a star, I'm just kidding. Clone or download the repo. It's free, it's out there for you to use, enjoy it. Go into it, code needle, create a virtual environment, activate it. I mean, all this stuff is in the README, which I included for you. And then install the prerequisites. Now you can run it. So open this up in your editor, then make sure you go into configs, put some files in there. You can use the ones that are already included, which is HTTP server or jQuery. Point it to where your files are. Like I said, use your own files. It's more fun that way. And then in the models folder, I already have some pre-configured. If you have these on your system, great. If not, then download them. This right here is the base URL for LM Studio with that port. So it's already configured for LM Studio. If you have that, great. If you have another tool like Olama, you can just replace that URL, point it to the name of the model, you know, do the thing. If you want a more detailed guide, let me know in the comments. But I think the README is pretty detailed enough already. Or just point your agent at the README and he'll do it for you. Now I'm gonna start things pretty easily here. I'm gonna use HTTP server. This right here on the command line is the config that I'm specifying right here. And this is pointing at the code file that I wanna run against my model that I wanna test. That's available right here in the fixtures folder. So this is the code that I wanna send to the LLM. It's not that long. It's only about, 1,300 lines of code. And then on the command line, I wanna select the model. Here I'm gonna do something real simple. Qwen34B 2507. This is different than the other Qwen34B because the 2507 version has 256 context length, 256,000 tokens. So we're good. We need to reload this model in LM Studio with the proper context length. 200,000 is fine. I'm gonna reload that and let's rerun that. Boom. I tested it with this one because it's the smallest model for this matrix, and this will basically run on any computer. It's like 2 gigabytes. For each of the 11 functions in that file, the harness drops the whole file into the model's context, and it asks it for the first 20 lines of every function, and then compares the answer. This one doesn't take very long, about 18 seconds, and here we are. 7 out of 11 passed. Let me show you what one of these looks like up close. So right here, here's the pass. The gray lines are a match. Those are actually in the file in that order. Orange is missing, and yellow is bad. Yellow is hallucinated. You might also see blue here. That's bonus. These are correct lines in order, but they're past the first 20 lines. Okay, so that's one model on one file. Now let me show you the rest of the matrix I ran ahead of time and what it actually tells you about local AI for code, because I didn't only run local models here. The first question I had is, does the benchmark actually work? So I ran it against frontier models, because if frontier models look broken on this thing, the bench is broken, and we're back to the drawing board. GPT 5.5 hits 213 out of 220 lines on HTTP server. 0 hallucinations. Very good. Claude, Sonnet 4.6. I didn't do Opus yet, but you can run it too. I can run it, whatever. Let me know in the comments. Sonnet 4.6 hits 207 out of 220 with 11 hallucinations. That's not 11. What am I doing? Anyway, the bench works. These are really high numbers. We're 97 and 94%. Now, can a model running on my laptop compete with these numbers? I started off with Qwen 3.6 35B. It's a 35 billion parameter model, but it's a mixture of experts with only 3 billion active parameters. And we've got 190 out of 220 with 28 hallucinations. It's not as good, but it's not terrible, right? Within 7 points of a frontier model. It fits on a Mac running offline, so that's what's hot right now in 2026. Next, I wanted to find out if file size matters, because HTTP server is a small Python file. Real code bases aren't that small. So what happens when you point this at jQuery, which is over 10,000 lines? GPT 5.5. Frontier model barely dips. It dips a little bit. Goes from 97% to 90%. Claude Sonnet 4.6 goes from 94% to 93%. So it's pretty flat, pretty good. But the local picture is where things change. Qwen 3.6 35B. This one drops from 86% to 78%. So the gap to frontier models doubles. It goes from 7 points to 15 now, the difference. And now, smaller models. Qwen 3 4B 2507 goes from 49% to 36%. Qwen 3.5 9B, for some reason, went up a little bit, but it didn't start out in a great place anyway. It started at 50%, went up to 68%. Now, originally I thought that the wall for small models was context capacity, but this version of the 4B, the 2507, it fits the file just fine. It just produced over 1,000 hallucinated lines for just 115 real ones. The wall isn't memory here. The wall is noise. The model is producing more invented lines than real ones. Okay, here is the leaderboard for jQuery. Every model I ran sorted by lines matched. Qwen 3.5 9B, that's this pink one right here. That's a dense 9 billion parameter Qwen model, gets 217 lines matched. This is out of 320, by the way. Qwen 3.6 35B, this one gets 249 lines matched. So bigger model wins. I wonder which one of those two is actually faster. It might be the bigger model in this case, because it only has 3 billion active parameters as opposed to the 9 billion in Qwen 3.5. So this is where the speed also, we need to do that comparison too in another video perhaps. Interesting here, Qwen 3.6 27B, which is not an MOE model, it's actually a dense model. That one gets about the same score, 250 out of 320, with even more lines hallucinated than Qwen 3.6 35B. And it's a much slower model, 27 billion dense. But also look at the hallucinations. So Qwen 3.5 9B, 318 hallucinations. That is a lot. Qwen 3.6 35B, 38 hallucinations. Okay, that's better. 44 hallucinations for Qwen 3.6 27B. But wow, that 9B model is unexpectedly bad with hallucinations. That's roughly 8 times worse than the next noisiest model in the entire matrix. And it's sitting right there, right in the middle of the entire leaderboard as if nothing's wrong. This is what you really got to watch out for. You might think, oh, 9B is fine. 217 out of 320. It's okay. Look at those hallucinations. Phew. That's bad. So even though hallucinations were pretty bad with Qwen 3.4b, the worst, they were pretty bad with Qwen 3.59b too, sitting all the way up here. You want to be down here near the sweet spot. High matches and low hallucinations, and we got obviously GPT 5.5 and Cloud Sonnet 4.6 there, okay? So yeah, we're still at this point, but we're getting close. Now this is a per function score here. Let's take a look at find. If you've ever used jQuery, you know what that is. The functions on the left are easier, the functions on the right are harder. Find is kind of in the middle, almost. Now, here, Qwen 3.59b scored 20 out of 20 for this function, but it emitted 85 lines, so 20 of them were right. 65 were wrong, or they were just made up. Qwen 3.6 scored 13 out of 20. It still passed because the threshold is 8, but it emitted only 14 lines. So almost all of them were real. More lines isn't more useful. If you'd actually use this output, you'd have to verify every line of the bigger blob anyway. Then you're back to needing the right model in the first place. So smaller isn't just less accurate, it's also noisier. Okay, but why does Qwen 3.59b fall apart? Is it just bad? Or is there something specific about this file tripping up? Well, this is the recall versus position in jQuery in this case. X-axis is the function start line in jQuery. So there's find at line 806, and here is parse HTML at line 10,142. And the Y-axis is the percentage of what expected lines the model got. And by the way, I'm going to include this as part of the repo so you can go dig into it and check it out yourself. This is an interactive chart. Let me show you the part that actually matters. So if we take a look at just Qwen 3.59b, it holds reasonably well, and then it kind of falls off the cliff here, then it does well again, and then falls off the cliff big time back here. And then at the deepest depth, it matched 20 out of 20. So it's kind of unpredictable. Qwen 3.635b is a little bit better when it comes to predictability. Same context, same prompt, stays almost flat after 2K, pretty much all the way across. Very different shape here. Now for context, here's Cloud Sonnet and here's GPT 5.5. Sonnet is blue, GPT is red. They both have a little bit of a hiccup, but most of the way across they are pretty flat. So what else does this benchmark catch? Let's go back to per function here. This is even more evident if you look at HTTP server position versus recall. And if we take a look at the frontier models, yeah, they nailed this. They destroyed this. And there's 9b, yeah, pretty bad. And 35b is decent, but it's got that big hiccup here. But for the most part, it does pretty well. Let's take a look at a dense model, 3.6, and that one does really well here. Wow. What about Gemma? Gemma does okay. It doesn't do amazing, but it does okay. Now, how does Gemma do in jQuery? Yeah. Let's take a look at per function score. Here's Qwen 3.635b. Look at that cluster. That's exactly 19. There's a bunch of them. These are 19 out of 20. That's 8 functions, all landing just one short of a perfect score. Well, it turns out Qwen 3.6 drops the leading tab on line 1 for every response. So no matter how well it gets the rest of the function, line 1 actually never matches. That's the same exact pattern as Gemma with the indentation thing, just a different model. It has a different quirk. Now look, I didn't program a check for either of those. The grader is kind of dumb right now. It diffs the lines, but that's it. But the grading has to be deterministic, I feel. So the behavior just kind of falls out of the data. Once you've seen it once, you will start spotting it everywhere. So I'd say Qwen 3.635b, when you see a pattern like this, they're pretty much on par for those functions with Gemma 4. So look, I'm not telling you use Qwen 3.6 over Qwen 3.5 because on different code bases, a different file size, a different prompt, the answer might flip. What I am telling you is this: don't trust the benchmark that gives you a single number. If you're going to be using an LLM to help you code, run this benchmark on your code and read both columns. One more shout out to the original creator or the inspiration for the idea, Ptorokokis. Sorry. Link to his channel down below in the description. Go subscribe. GitHub link for my version is also in the description. Pull it down, point it at your own code bases, and tell me what you find. And if you like this video, check out this one right here. Thanks for watching, and I'll see you next time.